Okay, so here, as our continuation, let's have the domain in the range. Okay, so the definition of the domain in the range. So domain is the set of all admissible values of x where x denotes the independent variable, while range is the set of all resulting values of y where y denotes the dependent variable. Okay, so how to determine the domain and range? Okay, so for the domain, to solve for the function in terms of x, we have here if the function is a polynomial, then the domain is set of all real numbers. Okay, so given if the function is a polynomial, obviously all the domain will be a set of all real numbers. If it is in rational expression uh, represented with the range of two functions, the domain is set of all real numbers, excluding those value of x that makes the function in the denominator equal to zero. Again, so the domain is the set of all real numbers except except for those values that is the denominator equal to zero. Then number three, if the function has a radical expression, we have here the nth root of the function, where n is an even natural number. The domain is set of all real numbers. That makes the function greater than or equal to zero. Okay, so if the index is an even natural number, we can say that the domain is set of all real numbers. But if n is odd, natural number, then the domain is the set of all real numbers. Provided, here again, the difference with the even and the odd, the even provided that the function be is greater than or equal to zero. To find for the range, if the function is a polynomial, consider the maximum and minimum values of the function represented by the turning points of the graph. Okay, so here, let's say we have a quadratic function. Okay, so given that we have a quadratic function, if the function is in this form, we need to identify its vertex form. Okay, wherein we have here y such that y is an element of real number wherein y should be greater than or equal to this one. 4ac minus b squared all over 4a when a is greater than 0. And y such that y is an element of real number wherein y is less than or equal to 4ac minus b squared all over 4a when a is less than 0. Okay, when a is less than 0. If the function is rational expression, simply solve for the values of x in terms of y. Okay, the values that makes the new denominator equal to 0 shall be excluded from the range. We can use the inverse function. But in the following rational functions that we're going to identify the domain and range, we're just simply recognize the asymptotes. Okay, the asymptotes and the whole for us to identify the range of the function. Okay, then lastly, if the function has a radical expression, the nth root of the function, where n is even natural number, the range is the set of all real numbers that makes expression the function be greater than or equal to 0. Okay, so given this, let's try to identify the following function, their domain and their range. So given that we have here 4x plus 5, we have the function 4x plus 5. Let's try to identify its domain and range. So if we're going to graph this, we'll have this one. Okay, actually this is a linear function, and linear function is a polynomial function. So if it is a polynomial function, we can say that the domain and the range of this is all real numbers. Okay, so we have here the domain x such that x is an element of all real numbers, and the range is y such that y is an element of all real numbers. Okay, so as you can see, we have here the linear function. Now, for us to identify the domain and range of a quadratic function, we need to recognize the vertex form. Okay, the vertex form by using the completing the square. Okay, by using completing the square here. So we have your y is equal to a quantity x plus b over 2a squared minus b squared minus 4ac all over 4a, wherein the vertex here is negative b over 2a, and then we have b squared minus 4ac all over 4a. Okay, so here in discriminant, the nature of the roots, we have b squared minus 4ac, wherein if d is greater than 0 and a perfect square, there are two rational solutions. And if d is greater than 0 and not a perfect square, there are two irrational solutions. If d is equal to 0, there are one rational solution. And then if d is less than 0, there are two imaginary solutions. Okay. In addition, the discriminant, the nature of the roots, we can identify the number of points that intersects to the x-axis. Okay, so given that d is greater than 0, the graph touch the x-axis at 2 points. Okay, so if you're going to solve for the discriminant, and the discriminant is greater than 0, the graph touch the x-axis at 2 points. If d is equal to 0, the graph touch the x-axis at only 1 point. And then if the discriminant is less than 0, the graph will never touch the x-axis. Okay, so please take note of this whenever you graph a certain quadratic function. And please take note again that we need to have the vertex form, okay, of the quadratic function to identify the domain in the range. Okay, let's have an example here. Given that we have x squared plus 8x plus 12, let's use the completing the square first. So in completing the square, all we need to do is to divide this middle numerical coefficient, okay, to 2, and then we square it. Okay, we raise it to the power of 2. Okay, so given that we have here 8, okay, so 8 divided by 2, that is 4, and 4 squared is 16. Okay, so we have here x squared plus 8x. And please take note, whenever we have the completing the square, we need to add and subtract. Okay, to preserve the equation. Okay, to preserve the equation. So we have here 8 divided by 2 squared. And then we also subtract it. Okay, let's simplify. 8 divided by 2 squared is 16. So we have here x squared plus 8x plus 16 plus 12 minus 16. So this one, this trinomial, we need to express this as a square of binomial. Okay, we need to express this as a square of binomial. So as you notice, x squared plus 8x plus 16 can be expressed as x plus 4 squared. Quantity x plus 4 squared. And then we have here 12 minus 16, that is just simply negative 4. Okay, that is just simply negative 4. So as you notice, we have now the vertex negative 4 comma negative 4. Okay, we have negative 4 comma negative 4. Okay, so the vertex of this quadratic function is negative 4 and comma negative 4. And as you notice, the value of a here is 1 and 1 is positive. Okay, so since 1 is positive here, we can say that this function, this parabola opens upward. Okay, if it is positive, it opens upward. So if we're going to graph that, we'll have this. Negative 4, comma negative 4 as our vertex. And then we have this. Okay, you can use your Desmos graphing calculator for you to graph it easily. Okay, but here we can have this sketch, just negative 4 comma negative 4, then extend it both sides. Okay, so as you observe, let's try to identify the domain and the range. Okay, so let's identify the domain and the range. In this case, as you observe, it extends both on the negative infinity and positive infinity of the values of x. Okay, so as you can see, it extends both sides. We can say that it is an element of all real numbers. Okay, this is an element of all real numbers. And then for the range, as you observe, it starts with negative 4. Okay, it starts with negative 4 and it extends upward. That means the values of y should be greater than or equal to negative 4. So we have here y such that y is an element of real number, wherein y should be greater than or equal to negative 4. So we have now the domain and the range. Another example. Given the function negative 2x squared plus 6x plus 5. So again, we're going to use the completing the square. But first, let's notice that here we don't have a as as 1. Okay, as you notice, we have here a as negative 2. Okay, so given that this is negative, obviously the parabola opens downward. And also this one, we need to factor out this. Okay, we need to factor out this negative 2. So let's factor out that. We have negative 2, quantity x squared minus 3x plus 5. Okay, so we identify this. Here, in the first two terms, we have the common monomial factor of negative 2. Now, let's perform the completing the square. Again, all we need to do is to divide this by 2 and then we square it. And please take note that the result should be multiplied to negative 2. Okay, the result should be multiplied to negative 2. So in this case, we have this 3 over 2 squared. Okay, and remember again, the result should be multiplied to negative 2. Okay, it should be multiplied to negative 2. Okay, so let's simplify. So we have here negative 2 quantity, x squared minus 3x plus 9 over 4. Okay, x squared minus 3x plus 9 over 4. Okay, so I forgot to put here a parenthesis. Okay, and then we have here 5 and then negative 3 over 2 squared is 9 over 4 times negative 2. Negative 9 over 4 times negative 2 is 9 halves. Okay, 9 halves. Okay, the product of this one is 9 halves. Okay, so let's simplify. Again, we can have the square of binomial here. X squared minus 3x plus 9 over 4 can be expressed as x minus 3 halves squareds. Okay, quantity, negative 2 quantity x minus 3 halves squared plus 5 plus 9 over 2 is 19 over 2. Okay, that is 19 over 2. Okay, so as you notice, we have now the vertex, which is negative 3 halves, 19 over 2. Correction, it should be 3 halves rather. Okay, because we need to equate it to 0. Okay, we need to equate it to 0. So we have 3 halves, comma 19 over 2. So if we're going to graph this, remember again, we have a negative a. So therefore, it opens downward. And we have this graph. Okay, we have the vertex 3 over 2, comma 19 over 2. Okay, now, for the domain, it extends both sides. both the negative infinity and the positive infinity. So therefore, the domain is an element of all real numbers. And take note that quadratic function is a polynomial function. And all polynomial functions, domain is all real numbers. So therefore, we have here x such that x is an element of real number. Okay, and then for the range, as you observe, it opens downward. So as you can see, it starts with 19 over 2. Okay, it starts with 19 over 2 and going downwards. So therefore, we can say that y such that y is an element of all real numbers such that y is less than or equal to 19 over 2. Okay, y such that y is an element of all real numbers wherein y is less than or equal to 19 over 2. Now, after the quadratic function, let's have the rational function. Okay, so for the rational function, please take note of the vertical and the horizontal asymptote. For the vertical asymptote, all we need to do is to identify the zeros of the denominator. While in the horizontal asymptote, we have here three cases. Okay, it has something to do with the degree of the polynomial of the numerator and the denominator. So given that the degree of the numerator is less than the degree of the denominator, the graph of the function has the line of y is equal to 0 as the horizontal asymptote. Okay, so given that n is less than m, the line y is equal to 0 or the x-axis is the horizontal asymptote. But if the degree of the polynomial of the numerator and denominator is equal, we're going to take the numerical coefficient, okay, the leading coefficient, and we have here y is equal to a over b, where a is the leading coefficient of the numerators, and then b is the leading coefficient of the denominator. Okay, so we denote or we have here the horizontal asymptote y is equal to a over b. And then for the third case, if the degree of the numerator is greater than the denominator, the graph of the function has no horizontal asymptote. Okay, it has no horizontal asymptote. So take note of that. Let's have an example. So given that the function is 5x plus 6 all over 2x minus 5, let's identify the domain and the range. Okay, let's identify the domain and the range. So first off, let's try to identify the vertical asymptote, the value of x that makes the denominator equal to 0. So if we're going to solve this, 2x minus 5, and we equate it to 0, the value of x here should be, is 5 halves. Okay, the value of x here is 5 halves. Okay, so x is 5 halves. So remember, this is the vertical asymptote of the function. So given this one, obviously, since this is the vertical asymptote, we can say that this is the only value. Okay, this is the only value that is not included to our domain. Okay, this is the only value that is not included to our domain. So x such that x is an element of all real numbers, wherein x should not be equal to 5 halves. Okay, so all real numbers except 5 halves. And then for the range, let's try to identify the horizontal asymptote. Okay, so in this case, as you observe, we have the degree of the numerator here as 1. Okay, so given this, we have 5x, and then we have in denominator also as 1. So the degree of the numerator and the denominator is equal. So therefore, all we need to do is to take the leading coefficient. Okay, all we need to do is to take the leading coefficient here, which is 5 halves, to have the horizontal asymptote. Okay, and our horizontal asymptote here is 5 halves also. Okay, so we have y is equal to 5 halves. Now, so as you notice, if you're going to graph the rational function, the only value of x that is not the only value of y rather that is not included here is the horizontal asymptote. Okay, it's the horizontal asymptote. So if that's the case, our range here is y such that y is an element of all real numbers except the 5 halves. Okay, except 5 halves. Okay, so therefore that is our domain and the range. Okay, so this one actually, this method is only applicable to this case of rational function. There are lots of different cases when it comes to rational function. Another example. So given that we have here the function 2x squared plus 7x plus 3 over x plus 3. So as you notice here, the numerator here is factorable. Okay, the numerator here is factorable. Okay, we can use the other types of trinomial, and we can say that the factor of the numerator here is, the factors are 2x plus 1 and x plus 3. Okay, the factors are 2x plus 1 and x plus 3. Now, as you notice, there's a common factor on both the numerator and the denominator. Okay, which is x plus 3. Okay, which is x plus 3. So if that's the case, we can cancel this out. And the only function here is 2x plus 1. Plus, but take note that the cancelled factor here will be a whole. Okay, it will become a whole. In this case, if we're going to find the value of x here, we have x be equal to negative 3. Okay, so x is equal to negative 3 for our whole. Okay, and then for us to identify the ordered pair, okay, of that whole, let's substitute this negative 3 to our remaining function, which is 2x plus 1. So if we're going to substitute that, we have 2 times negative 3, that's negative 6 plus 1. Okay, so the value of y there is negative 5. So therefore, there's a whole at negative 3 comma negative 5. Okay, there's a whole at negative 3 comma negative 5. So as you notice, as we simplify the function, we have 2x plus 1. This will lead to a linear function. However, there's a whole at the point negative 3 comma negative 5. So if that's the case, let's identify the domain and the range. So since this is a whole, we all know that it is excluded. Okay, it is excluded. So we can say that since this is a linear function, it is an element of all real numbers for both the domain and range, except only for the whole. Okay, so the domain here is an element of all real numbers except to negative 3. And then the range, all real numbers except to negative 5. Okay, so in this case, this type of rational function, we can identify the whole. Okay, we can identify the whole. Okay, and actually, we're going to discuss different cases in rational function in different unit, okay, of college and advanced algebra. Okay, another one, we have here a radical function. So given here, we have a radical function, negative square root of x minus 1. Okay, negative square root of x minus 1. So as you notice here, we have odd function. Okay, so given that, let's try to identify the value of x here. Okay, let's try to identify the value of x here. So given that we have x minus 1, it should be greater than or equal to 0. Because if it is less than 0, obviously this will be an imaginary. Okay, so therefore, let's equate this x minus 1 to greater than or equal to 0. Okay, it should be greater than or equal to 0. So if we're going to solve this, x should be greater than or equal to 1. Okay, x should be greater than or equal to 1. Okay, now, so given that the domain is x should be greater than or equal to 1, let's have the range. Okay, so given that we have it should be greater than or equal to 1 here, let's substitute. Okay, so if we're going to substitute that 1 minus 1 is 0. Okay, 1 minus 1 is 0. So that is 0. Okay, and then another one, let's say we substitute 2. Okay, so we have here 2 minus 1 is 1. The square root of 1 is 1. Then we have here a negative value. So it produces negative 1. Okay, so we have 0, we have negative 1. Let's say another one, let's say we have here uh, 3. Okay, 3 minus 1 is 2. The square root of 2 is square root of 2. Okay, that is negative square root of 2. So as you notice, it's a negative value. Okay, it produces negative value. So therefore, we can say that y such that y is an element of all real number provided that y is less than or equal to 0. Okay, so if we substitute the values of x here, it produces a negative value. Okay, so therefore, we can say that y is less than or equal to 0. Another example, given the function is square root of 9 minus x squared, same procedure, we're just going to solve for the value of x here that is greater than or equal to 0. So if we're going to solve that, 9 minus x squared is greater than or equal to 0. Okay, so let's factor this one. 9 minus x squared is the difference of two squares. So the factors are 3 plus x, and then we have 3 minus x. Okay, so if we're going to separate this, we have here 3 plus x is greater than or equal to 0. So solving that, x is greater than or equal to negative 3. And then another factor, 3 minus x, is greater than or equal to 0. We can observe that x is less than or equal to 3. Okay, x is less than or equal to 3. So as you notice here, x is greater than or equal to negative 3, but also x is less than or equal to 3. So with that, the domain is x is between negative 3 to 3. Okay, x is between negative 3 to 3. Okay, so with that, let's try to identify the range by substituting the minimum and the maximum value. Okay, by substituting the minimum and the maximum value of negative 3 and 3. Okay, so let's substitute. So given that we have here as negative 3. Okay, we have here negative 3 squared. And negative 3 squared is 9. Okay, that is 9. Negative 3 squared is 9. So 9 minus 9 is 0. Okay, 9 minus 9 is 0. So if that's the case, we can say that we have 0. Okay, and another one, still with this, with 3, 3 squared is 9, so 9 minus 9 is 0. Okay, so now let's try to identify its halfway. Okay, let's say from negative 3 to 3, there's a value of 0. Okay, there's a value of 0 here. If x is equal to 0, so we have here 9 minus x squared, or 9 minus 0 is 9. The square root of 9 is 3. Okay, the square root of 9 is 3. So as you notice, we have here the values from 0 to 3. Okay, we have the values from 0 to 3. So if that's the case, we have y such that y is an element of all real numbers, wherein y is from 0 to 3. Okay, wherein y is from 0 to 3. Okay, so here, for us to identify its values, we need to substitute, okay, this the values of x here. Okay, in this case, we meet halfway and we observe if it is 0. Okay, so for you to understand it more, let's have the graph. Okay, let's have the graph of this. Okay, so as you notice here, we have the function, the parent function square root of x, and then we have your negative square root of x minus 1. So as you observe, the domain x is greater than or equal to 1. Okay, the values are x is greater than or equal to 1. And its range, as you notice, it's only negative values. Okay, so y is less than or equal to 0. Okay, and then here, the graph of the square root of 9 minus x squared is actually a semicircle. Okay, it's a semicircle. Okay, so as you notice here, as you observe, we have here from negative 3 to 3 as our domain. And then for our range, it starts with 0 and it ends with 3. Okay, it starts with 0 and it ends with 3. Okay, that is our range. Okay, let's have last example. Okay, we have your last example. So given that the function here is a piecewise function, so we have here 2x minus 5 as the first subfunction if x is not equal to 2. So all values of x except 2. And then we have here a constant function 0 if x is equal to 2. Okay, if x is equal to 2. So as you notice, the values of x here, it's all included. Okay, it's all included. Here, all values of x except 2. Here, only 2. So if that's the case, the domain here is element of all real numbers. And then for the range, as you notice, if you're going to substitute that, it will produce you all the possible values of all real numbers. So we can say that y, such that y is an element of all real numbers. Okay, so y such that y is an element of all real numbers. So here, as you notice, we have different types of function. You need to recognize its properties for you to identify the domain and the range.